Now, first of all, when I say the joke, why does Waldo wear stripes? I realize that maybe not everyone in the room knows who Waldo is. So, do you all know who Waldo is? Where's Waldo? There is this thing called Where's Waldo? There were books. Well, I suppose they still are books. And it would publish or it'd show this guy right here. There's Waldo, and he wears a red striped shirt. And then they would publish a scene like this one that just has a massive amount of people and things going on. And you're supposed to just look at that and find Waldo. So does anybody see Waldo? I realize it might be tough where you're sitting to actually see him because it's so tiny up there, but I don't see Waldo, but apparently he's in there somewhere. Okay, well, that's enough. Anyway, that's called Where's Waldo? And the joke is, why does Waldo wear stripes? Because he doesn't want to be spotted. A real knee slapper there. All right, let's go ahead and continue. Where did we leave off? Last time we finished through these equations, and then we looked at solving inequalities. We talked about above and below. So,
distance equals rate.
Right, I think, yeah, we're right here. We're looking at a couple of word problems. Now, here's what I'd like to do today, just so you know. We're going to do these couple of word problems, which are always very exciting. And then we're going to look at the practice test together, and I'm going to highlight a few problems in the practice test that I think that it would be helpful to have a little bit more experience with. So we'll do that. We'll do these last 4 word problems, and then we will look at the practice test. And then you'll all go home, enjoy your long week, and then come back and take the test. Okay, everyone ready? Does everyone have a photocopy, by the way? Everybody has it? Because I have a lot of extras. Okay. So Carl and Mike start a 3-mile race at the same time. So we all know what that looks like. They're standing there, they say go, and then they start running. Mike can run the race at a 6-mile-per-hour. Wait, he can run the race. No, he ran the race at 6 miles per hour and finishes the race 10 minutes before Carl. How fast does Carl run? So this is a really interesting question. We're saying, and let's start by drawing a picture. So we've got a 3-mile track. So that's distance equals 3 miles. And we've got Mike and Carl starting here together. And we have Mike running at 6 miles per hour. So there's his rate equals 6 miles per hour. And Carl is running at some rate we don't know, so maybe we can just call that R. Maybe not R, because I just called his rate R as well. How about we'll just call him R equals X. There we go. His rate is X miles per hour. And we also know that Mike finishes 10 minutes before Carl. Now, how do we write that down? So Mike's time, we'll call that time equals T. Well, maybe not T. Well, let's just see. Let's say Carl is his time. How should we write that down? We know that Mike finishes 10 minutes before Carl. So we have 2 choices. We can either say that if Carl took T minutes, then Mike took T minus 10 minutes, right? Because he finished sooner. Or we could say that if Mike's time is T, then Carl's time is T plus 10. Right? Or those are equally arbitrary choices that we could make. Does anyone have a preference for what you like? Should we say that Carl took 10 minutes more than Mike? Or should we say that Mike took 10 minutes less than Carl? You think one of those ways is better than the other? Anyone want to choose? T minus 10?
It's already on the board.
Sure, it's already on the board. See, I might say I prefer T plus 10 because then it's plus, and I like to do my algebra with pluses instead of minuses. But, you know, it's an arbitrary decision. Okay, how does everyone feel about what I just wrote on the board? Basically, I just made a little drawing to capture all the information from the problem. So this is all the information from the problem. Now, why did I even choose these things? There's a formula called D equals RT, which I'm presuming that you've all seen quite a few times in your life. Distance equals rate times time. And it's just an equation that we can use to manipulate expressions. So what can we do here? We could make up 2 equations, one for Mike and one for Carl. So if I have Mike and I have Carl, Mike's equation would be D equals, I'm going to write this differently. I'm going to write Mike right here and say his D equals RT is what? His distance was 3 miles, his rate was 6, and his time was t minus 10. And then we have Carl, and he also has d equals RT. And his d was also 3, and his rate was x, and his time was t. Well, what do we think? We're just kind of playing around right now. Okay, we're playing in the space of writing down things that we know. Would it be possible to solve for anything right now?
Yes.
What could we solve for?
It's solved.
Yeah, we can solve for time for Mike, right? Because we actually know 2 pieces of information for Mike, and we're trying to solve for this t minus 10 thing, but since we know that he ran 3 miles at 6 miles per hour, we should actually be able to solve for his time right now. So looking right here, we could go ahead and solve for that t value. So we can go ahead and distribute our 6, and that'd be 3 equals 6t minus 60. Move our 60 over to the other side, and that would give us, uh-oh, everyone stop. Where have we already gone astray? It's talking about 6 miles per hour, and then it gave us the time as 10 minutes. Is this a problem? They're giving it to us in miles per hour.
To convert the mile per hour to 10 minutes, or we have to put 10 to the fraction of 6 miles per hour.
Yeah, one way or the other, if it's in miles per hour, then we can't say 10 minutes. We'd have to say how many hours that is. Or if we're saying 10 minutes, we couldn't say miles per hour, we'd have to say miles per minute. So either way, those units have to match. So let's go back now and think about that. We're going to have to erase a few things and rethink how we're doing this problem. If it's already in miles per hour, I think it would be easier to change 10 minutes into hours. Because after all, are we all familiar with miles per hour? Yes. Are you familiar with miles per minute? Not so much. So what is 10 minutes as hours? How long of an hour is that? How long of an hour is 10 minutes? It's a fraction, right? What?
1/6.
Yeah, 1/6. And how would we do that? We'd say 10 minutes out of 60 minutes. And that's how much of an hour it is. And so that's 10/60ths, which is 1/6. So now that has now taken us from 10 minutes is actually 1/6 of an hour. Okay, so now let's go back. We caught our goof there. It should be, we have to match our minutes to, I'm sorry, we have to match our units. What we're really saying now is that Carl is t minus 1/6 of an hour. And so now that's 1/6. Solving a word problem can be like this, a little revisionist, where like you start the problem and you're like, oh, okay, no, let's not go that way. And then you try it a different way and they're like, oh, okay, no, let's not go that way. You try it a different way. And so it's important to know that sometimes that's just how it goes, that you're playing with the word problem, trying to figure out which way to go. Okay, now I think we're definitely on track. We're matching our units. Well, now we can go ahead and solve for his t. So again, we distribute. 3 equals 6t minus 6 times the 6 is just 1. So then we add the 1 over, and we get, oops, 1. We get 4 equals 6t, and then we divide up to 6. And our time is 4/6 of an hour. 4/6 of an hour, which is 2/3. How much of an hour is that?
40 minutes.
Yeah, that'd be 40 minutes, right? So 2/3 of an hour, 2/3 of 60 minutes would be, over 1, that'd be 120 over 3, which is 40 minutes. So that's what we found out so far about Carl. Sorry, Mike. 40 minutes. And now that we know, so it was 2/3, and we just went ahead and changed it in our mind back to 40 minutes. So now we know that Mike's time was 40 minutes, and we originally wrote that as t minus 10, meaning he ran it 10 minutes faster than Carl. So how long did Carl run?
50.
Yeah, 50 minutes. So if Mike, he was faster, he did it 10 minutes faster, so Carl we now already know is 50 minutes. How can we do that? Well, we can still do that by coming back now, taking our t value and plugging it into the equation that we have for Carl, right? Rather than just doing it off the top of our heads. Now we can say 3 equals x, which is Carl's rate. Because after all, we don't want to know how long it took Carl. The question was, how fast does Carl run? So now we come over here, we plug in our 2/3 for what we solved t to be. And now we can go about solving for Carl's rate. So x is being multiplied by 2/3. How do I get rid of the 2/3? What's that, Jackie? You multiply by the reciprocal. You can either divide off the 2/3 or you can just multiply by 3/2. So we're going to multiply both sides by 3/2. And that gives us x equals 9/2, which is x equals 4.5. And what unit is that? What's the unit on this x value? Yeah, miles per hour. So now we know everything about these two runners. We know that Mike takes 40 minutes, Carl takes 50 minutes. Mike runs at 6 miles per hour, and Carl runs at 4.5 miles per hour. Yep. How does everyone feel about that particular solution? We started with solving about Mike, because that was something that we could solve for. And then we came over here. Now what made that a little awkward? Let's look at our choices again. That's because we chose to write it as t minus a sixth for Mike. But since Mike is the person we actually knew about, what if we now change how we think about that and say, what if we let Mike be the r equals 6 and t equals t, whereas Carl is rate equals unknown and t equals t plus 10 or plus a sixth. Would this be helpful to try it that way instead? We still know that our distance is 3. Because now for Mike, we could go ahead and say Mike is d equals rt, and so his distance is 3, his rate is 6, and the time we're just solving for t. So t is simply 3/6, which is 0.5 of an hour, which is 30 minutes. Hey, wait a minute. That seems to have changed something. If we just change that around, did we change that in the wrong direction? Mike finishes 10 minutes before him. Why did we get a different answer? Was that not equally valid, what we just did? Changing, solving for his time and then adding 10 minutes to Carl? Isn't that what it was? He finished 10 minutes before him, so Carl finishes 10 minutes after him. Why was it different? What's that?
They're going different off the hour.
Well,
Mike's time can't change.
yeah, Mike's time shouldn't change. Did we do something early on that boy, I'm really torn as to why that should have made a difference. Theoretically, we should be allowed to either say that Mike ran 10 minutes slower, yeah, or that is Mike ran faster and then Carl used more time. Anyone have any thoughts? Because in the beginning, we said that it should be the same either way. Well, it was definitely 3 miles. We ran 6 miles an hour. And he finished 10 minutes before Carl. That was our 10 minutes or 1/6. So that was t minus that, where t is Carl's time. Oh, I know what we did. Oh, silly me. T, when we solved for t, what did we solve for? T was who? T was actually Carl. that t that we solved for represented Carl. And therefore, how long did it take Mike take, or how long did Mike take? 10 minutes less than that, which is 30. All right, there we go. Now we have some nice clarity that both approaches do really work, and we have to be really careful about where we write our answers down. All right, now it all makes sense. Again, this is how a word problem could go. You start one way, and then you have to go back, think about it a different way. You try two different approaches, and the answers don't agree, and then you have to look and find your mistake. Okay, but now it's completely done. So now we know that he was 30 minutes, which is 0.5 of an hour, and now I can come over here and double check Carl, who was t equals RT. And now he's going to be the 3. His rate, we don't know, but his time is 0.5 plus a 6th. Now, his time is 0.5 plus a 6th. So now I actually have to do some fraction work to add those together. So I'm going to multiply top bottom by 3. And that gives me 3/6 plus 1/6, which is 4/6. And that's going to be my time for Carl. And then again, x, you can divide off the 4/6 or multiply it by the reciprocal, 6/4. And so we get x equals 18/4 or 9/2 or 4.5. So we end up with the same answer, that he was running at 4.5 miles per hour. Okay, so there we go, folks. You got to see that problem twice. Those were two different possibilities. They both should end up with the same answer. And just as an encouragement to you, it's often a good idea to try to solve the problem twice. If you solve it in two different ways, first of all, you're kind of checking your work, that you should arrive at the same answer. And then if you come up against some incongruity like we did, you have to go back and look and find your mistake. Okay, so that's number one. Why do you suppose that word problem was in here? In this particular problem, or in this problem set. We're talking about rational expressions. Was there anything about d equals RT that was rational? No. But it was a nice warm-up problem thinking about d equals RT for the next problem, which I think is actually going to utilize a fraction of some sort. So now let's go ahead and take a look at number 2. One day, Donnie observes that the wind is blowing at 6 miles per hour. An unladen swallow nesting near Donnie's house is 3/4 of a mile down the road in the direction of the wind, turns around and returns exactly 4 minutes later. Oh, there we go. I thought that was a typo for is. That's actually the word flies. Everybody write flies. That means an unladen swallow nesting near Donnie's house flies 3/4 of a mile down the road in the direction of the wind, turns around and returns 4 minutes later. What is the airspeed of the unladen swallow? And that is, airspeed is how fast the swallow can fly. Now, by the way, does anyone recognize this word problem? They're talking about unladen swallows. Anybody? Okay, well, just to give you the context, because sometimes math textbooks are funny. This is YouTube, Monty Python, Holy Grail, Swallow. This one, now, I don't know if it's going to play at any volume. Has anyone seen Monty Python in the Search for the Holy Grail? A couple of you? All right, well, no, the volume is not going to play, but there's this hilarious opening scene. It is the opening scene of the whole movie where they're talking about how quickly birds can fly. And they're like, well, is it an unladen swallow or is it carrying something? Because birds will fly slower if they're carrying something. Anyway, if you're interested, it'd be worth watching the scene. You can just look up Monty Python unladen swallow. It's pretty funny. So that's what they're talking about. All right, so now let's write out what this word problem looks like, okay? Now again, you've got a bird, and the bird, okay, this is number 2. The bird starts somewhere, flies somewhere else, and then turns around and flies back. So let's read the word problem again and lay in all of our information. One day, Donnie observes that the wind is blowing at 6 miles per hour. So let's go ahead and say that the wind is blowing in this direction. So that's my wind, and the rate of the wind is 6 miles per hour. An unladen swallow nesting near Donnie's house flies 3/4 of a mile down the road. So what we have then is the first thing the swallow does is fly 3/4 this way. So the distance is 3/4 of a mile. And by the way, is our unit good so far? We're in miles per hour. And is our distance in miles? Yes, okay, that's good. So that's so far the first thing that happens, is this bird flies 3/4 of the mile down the road in the direction of the wind. So you'll notice that right now he's going with the wind. Now what does that tell you about the speed of the bird? That the bird's already flying at a certain pace, and then he's going with the wind. How fast is he going? Faster or slower? Now the wind is helping him go faster. So as a matter of fact, whatever the speed of the bird is, it's now going 6 miles per hour faster than what the bird would ordinarily fly if the bird was just flying in still air. Okay, so then that's the rate. Do we know how fast the bird flies all by itself? Yeah, we actually don't. In fact, that's the question. What is the airspeed of an unladen swallow? And airspeed is the speed that the swallow can fly in still air. Gosh, that's another type of fly in still air. So we don't know how fast the bird can fly all by itself. So let's just go ahead and say the rate of the bird is X miles per hour. That's the rate of the bird, is X miles per hour. So in the wind, the rate of the bird is actually X plus 6. All right, so we're saying a lot of things right now. On the one hand, the bird flies 3/4 of a mile. The bird all by itself would be going X miles per hour. But with the wind, in fact, better than in the wind, I'm going to say with the wind. With the wind, the bird can go X plus 6 miles per hour. Okay, so then what does the bird do? The bird turns around and returns exactly 4 minutes later. So now the bird is coming back, and now against the wind, how fast is the bird flying? It can still go X miles per hour, but it's going against the wind, which is slowing it down. So fast, how fast is the bird going now? Yeah, X minus 6. So the rate of the bird going with the wind was X plus 6. It was going 6 miles per hour faster by the wind. But coming back, it's X minus 6 because the wind is pushing against it and it slows him down. Now, what we know here is that the overall total time, okay, the total time for the whole trip, total trip time was 4 minutes. So we have to change that unit, because that's minutes, but we were working in miles per hour. So what is 4 minutes? That's really 4 minutes out of 60 minutes, which is really 1/12 of an hour. Wait, 1/12, 1/15. Right, and you can write it as a decimal if you'd like, but I think if you do it as a decimal, you end up with a repeating decimal. What did you say? 0.066666666. So probably easier if we just leave it as 1/15. So let's see. The one thing I'm going to do here is I'm going to take away how I wrote r equals x right there. And I'm going to say speed of bird alone equals x miles per hour. That's just kind of a note I'm making to myself. Okay, so how does our diagram look? We have the fact that the wind is blowing this way at 6 miles per hour. The bird takes off and flies this way 3/4 of a mile. The speed of x plus 6. The bird turns around and flies back this way, still 3/4 of a mile. This time the speed of x minus 6. And both of those trips together, the total trip time is 4 minutes. Now, is that really what it says? Did we capture all the information from the problem? One day, Donnie observes that the wind is blowing 6 miles per hour, and unladen swallow nesting near Donnie's house flies 3/4 of a mile down the road, turns around, and returns 4 minutes later. Yeah, so the whole thing was 4 minutes. What is the speed of the unladen swallow? So we're trying to solve for this x, and that's what we have. So now what do we do? We need to write some sort of equation, right? And the one thing that we know for sure is that the total trip time should add up to be 1:15. Well, do we know how long the first part of the trip took? Let's call that T1. Or we could call it T with and T against. So do we know how long T with took? Do we know how long it took him to fly with the wind? No. Do we know how long T against took? How long it took to come back? No. Should those two trips take the same amount of time? No, because He went much faster going and then slower coming back. So those two times are different. But what I'd like to suggest is that if we know that the total trip time is 1/15 of an hour, the time with the wind plus the time against the wind should be equal to the total time. How does everyone feel about creating that equation? We're claiming this is the equation we're going to use to solve the whole problem. Why? Well, because the total trip time is the other piece of information that they gave us, and we need to use it somehow. And so by writing it out like this, we could figure out how long it took him to fly with the wind, how long it took him to fly against the wind, and add them up to equal the total, which was 1/15. So then what do? Do we have an equation for t? Because right now what we have, if we have d equals rt, this is a formula that's solved for d. So do we have a formula that says t equals? Because we'd like to be able to plug in something for this time and for that time. And we already know what we can plug in for this time. It'll just be 1/15. Right, exactly right. We can solve for either r or t. So starting with this basic equation, I can solve for t by saying t is being multiplied by r, so divide by r. And now I have that expression for t. T equals d over r. So I can say t equals d over r. But just so you know, I could just as well solve for r if I wanted to. So I could take d equals rt and solve for r. R is being multiplied by t. I could divide off the t. And then I would have the equation r equals d over t. So either way, what we're actually looking at is three different equations. You actually have d equals rt, or t equals d over r, or r equals d over t. So it's helpful to notice that you can rewrite the formula in any way. So now we have our basic equation here of time with and time against. We can rewrite time as d over r. So let's do it. Right here for time with the wind, I'm going to change that into distance with the wind over rate with the wind. Then I'm going to add that to distance against the wind over rate against the wind. There. So notice I'm using these words with and against as like a little subscript to let me know, a little more specifically what numbers I'm going to plug in. So what can we plug in now? What was our distance with the wind? How far did he go in one direction? No, we do know it. Yeah, 3/4. It went 3/4 of a mile that way and 3/4 of a mile coming back. So the distance with the wind was 3/4 of a mile. The distance against the wind was 3/4 of a mile because he flew 3/4 either way. Now what about his rate with the wind? How fast did he go? The rate with the wind. That was the x plus 6. And then the rate against the wind? That was the x minus 6. And so now we have this really nice rational equation that we'd like to solve. The whole thing now is in terms of the one variable that we don't know, which is the speed of the bird. Okay, well, that was a whole lot of work to get ourselves to the point where we now have an equation we could solve. Notice that in the previous problems that we did, they would just give us equations and then say, here you go, here's an equation, solve it. Whereas in a word problem, the whole purpose of a word problem is to give you a word problem and you have to then figure out how to represent the problem in an equation. And that's the first 50% of your work. And then actually solve this equation. And that's the second 50% of your work. So what are we going to do? Yeah, we want to cancel out the denominators. Now, what else can we do here? Like maybe a little bit of work right up front. Does anyone like seeing the 3/4, or should we write 0.75? I bet a lot of us would prefer 0.75. Now that I've done all that work, but I need more room to finish writing it all, I'm going to come over here and start up top. So this is just a matter of cleanup now. So I have this equation, 3/4 over x plus 6. And then I have 3/4 over x minus 6. And all that is 115. So what can we do to make this equation more palatable, more nice? The first thing we could do is just change the 3/4 to 0.75. And maybe everybody likes that. So 0.75 over x plus 6 plus 0.75 over x minus 6. Now, is there something else we can do to make this equation nicer? We've got this 1/15 over here, which we know is 0.06666 repeating. Can I do anything to get rid of that fraction? Yeah, what if I multiply both sides by 15? If I multiply both sides by 15, I'm going to multiply this side by 15, and I'm going to multiply this entire side by 15. That would be really nice, because then that would cancel out, and I would just have equals 1. And then over here, the 15 would get distributed to 0.75, which, checking on your calculator, that comes out clean. That's just 15 times 0.75. Oh, that doesn't come out clean. That's 11.25. Well, in any case, let's do it anyway. So it's 11.25 over x plus 6 and 11.25 over x minus 6. Now you might be asking yourself, what are we doing right now? Well, we're just kind of making the equation look nicer. We know we got rid of the 3/4, we got rid of the 1/15. Now we just have, this equation. Okay, so now how do we solve this equation? We want to eliminate those denominators. And that denominator is x plus 6, this denominator is x minus 6. If we multiply through by the least common denominator, what would be our common denominator? It would be x plus 6, x minus 6. So remember, and here, maybe I'll come over here just to demo that. If I had 11.25 over x plus 6, is it the same order? Yeah. And then 11.25 over x minus 6. And then I'm going to say that's 1 over 1. Well, this denominator has a plus 6, this denominator has a minus 6. So this fraction would want to have an x minus 6. So I can put it there. And this denominator would want to have an x plus 6. So I put it there. And this denominator would want to have both. So I put x minus 6, x plus 6. In any case, what is our common denominator? X plus 6, x minus 6. So all of that was just to demonstrate that our common denominator really is x plus 6, x minus 6. So we're going to go ahead and multiply through the whole thing times x plus 6, x minus 6. And as you multiply that across to all three, then what will cancel? What cancels in the first one? The x plus 6, leaving behind the x minus 6. So now we have 11.25 times x minus 6. And then in the second fraction, when you multiply it across, what cancels? Yeah, the x minus 6, leaving behind the x plus 6. So now you have 11.25 times plus 6. And then all the way over on the other side of the 1, I have that entire expression, x plus 6 times x minus 6, all the way over there. All right, so at this point, we do have a standard equation. There's no more denominators. And we distribute everything and FOIL that out. And then we'd be able to collect all of our terms together and solve. So let's distribute our 11.25. So we'd have 11.25x minus 6 times that. Let's multiply that out real quick. 11.25 times 6, that's minus 67.5 plus 11.25x plus 6.75 equals x squared. By the way, what's x plus 6 times x minus 6? It's x squared minus 36, right? That's a difference of squares. When you multiply conjugates, you get a difference of squares. You can FOIL the whole thing out, but that is a difference of squares. And over here, these 67.5s cancel out. And when we add these together, we get 22.5x equals x squared minus 36. What do we do next? We want all of our terms on one side. I already have my x squared over here, so I'll go ahead and just bring the 22.5x over. And that gives us 0 equals x squared minus 22.5x minus 36. Now at this point, we just have to solve that using the quadratic formula, unless someone thinks it's factorable. I don't think it's factorable, because what would you multiply to make 36 to add to make 22.5? So assuming that it's not factorable, then one thing you could do right now is check Desmos and actually find the x-intercepts, because remember, we're always allowed to just graph it and look at the x-intercepts. So we have x squared minus 22.5x minus 36. And so looking at my graph, there are 2 solutions. One is negative 1.5, and the other is 24. So let's just jot that down real quick, just so we all know what the answer is. My answer for x is going to end up being negative 1.5 or 24. So before we actually finish, let's look at those 2 answers. What could the speed of the bird be? Could it be negative 1.5? No, that doesn't make any sense. Or could it be 24? Yeah, that could make sense. So we still have to go back and finish, but at least those numbers seem reasonable and plausible. So what would we do? We would just do the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And so we plug in negative b, a, c all over a. And that would give us 22.5 plus or minus. Now that big square root, let's calculate everything in there. That's 22.5 squared plus 4 times 36. I got 650.25 all over 2. And that gives us 22.5 plus or minus, I believe that's square roots. It does, 25.5 all over 2. Now, folks, I realize this is a very long problem, isn't it? We've been at this for a while. We're just following through on this chain of reasoning to see where it leads us. We started by mapping it out with a diagram so we knew what the bird was doing. We then created our own equation that we could use to solve it. And then we actually plugged everything in and started solving it by getting rid of the denominators. Now we're doing the quadratic formula, and we're down to just the last 2 possibilities, which is either 22.5 plus 25.5 over 2, or 22.5 minus 25.5 over 2. And those 2 possibilities are, can you add them together? 22.5 plus 25.5, 48 over 2, which is 24, or 22.5 minus 25.5 divided by 2, which was the negative 1.5. Okay, so going back to the very beginning here, what we just found out was that the speed of the bird is either negative 1.5 or 24. Now, in terms of realistic, does it make sense that the bird's speed is negative 1.5? No, and so we would cross that one out and say that's extraneous. That is a solution that algebra led us to, but in terms of what we consider a reasonable answer, we were looking for a positive speed of the bird, and so we're only looking at the answer of 24. Now here's a big question. Is our answer right? Is it true that if I plug 24 into this equation, that it would be correct? Can we find out? Yeah, we can just plug it in and see. So if I plug it in, that'd be 0.75 over 24 plus 6 is 30, plus 0.75 over 24 minus 6 is 18. And then I wonder, does that equal 1/15? So let's find out. Because if we found the correct answer, it should all work out. So I'm going to do 0.75 divided by 30 plus 0.75 divided by 18. That gives me 0.06 repeating over here. And then 1 divided by 15 is 0.06 over there. So yeah, the answer actually works. That was a considerably long word problem to get all the way through. And so I'm thinking about you all and wondering how you're feeling emotionally about all this. Because sometimes doing a long word problem can be draining. But on the other hand, maybe you're like, okay, well, that's fine. It's a long problem, but that's just how it goes. Any thoughts or questions? All right. Well, those are two D equals RT problems for you. Let's go ahead and turn the page, try these last two. I will come over here so that stays up for a minute. All right. So other than D equals RT, okay, that's one particular formula you can use to start a problem. There is also a concept known as a shared work situation. Shared work is exactly what it sounds like. Instead of you doing household chores all by yourself, you and your roommate or you and your partner do the chores together. And in any project, like raking all the leaves in your backyard, here, I'm just going to give a silly example. Let's say that it takes me 2 hours to rake my entire backyard. Whereas it takes my toddler 5 hours to rake the entire backyard. Why does it take my toddler 5 hours to rake the backyard and it only takes me 2? Because they're a toddler, right? I mean, they're not necessarily staying on focus or on task, and they're smaller, it takes them more time. Anyway, if we work together, how long would it take to rake the yard? Like if we actually go out there together and we're both raking, how long will it take? What do you say? How much? Like an hour? Yeah, I mean, it's got to be less than how long it would take me by myself. Because if it's just me by myself, it'd take 2 hours, but I am getting help, albeit from a toddler, I'm still getting help. So when I merge these two numbers together, I should get something less than 2. You know, maybe 1.75. You know, how much help is my toddler actually giving me? I'm not sure. But this is what we're trying to calculate, is that if 2 people work together, how long will it take them if they work together? And the answer should always be less than the smallest number, right? Because ultimately that person is getting help. And so that's what this shared work formula does for us. The x over a plus x over b equals 1. X is how long it takes them to go together, whereas a and b are the time that each individual person needs to do their job. So in my particular problem right here, the one I just made up, I would say, how long will it take us to work together? I don't know yet, but it would be x over 2 plus x over 5 equals 1. And that would be the shared work formula. So it took me 2 hours, it would take my toddler 5 hours, and together I can solve for x, and that would be how long it takes us to go together. So let's just do that real quick. The common denominator would be 10. So I'm going to go ahead and multiply all the way across by 10, because multiplying through by 10, 10 over 2 would be 5x, and then 10 over 5 would be 2x, and then that equals 10, and then 5x plus 2x is 7x equals 10, and divide up to 7, and that means that x is 10/7, which is really 1 3/7, which is, let's find out, 3/7. That's 1.428 hours. So that's fantastic, right? It would take me 2 hours to work alone, but with my toddler coming out there, it's only going to take us a little less than an hour and a half to work together. All right? So the expectation is this is just another formula you'd memorize, just like D equals RT. So this is your shared work formula. Everybody ready to try number 3? Let's take a look. It says a faucet can fill a sink in 5 minutes. So let's draw a picture of that. This is number 3, and I have a sink and a faucet. Does that look amazing? That's my sink with a faucet. So a faucet can fill a sink in 5 minutes. So I'm going to fill in 5 minutes. While the drain can empty the entire same sink in 8 minutes. So now I've got my drain down here, and that's going to drain the water. So that's going to drain it in 8 minutes. So first of all, if it only takes 5 minutes to fill, but it takes 8 minutes to drain, and I turn on the water, will the water slowly start filling up, or will it drain as quickly as the water goes in? Because I'm sure you've experienced both. You've been at a sink where you can turn it on full force, and the water just drains as quickly as it goes in, and the sink never fills. On the other hand, I'm sure you've been at a sink where you turn it on, and it drains so slowly that the water starts filling. And so you have to turn off the water. Have you experienced that? Okay. All right, so what's going to happen here? Is the water going to drain as quickly as it comes in, and the sink remains empty, or would it slowly start filling up? Yeah, it would slowly start to fill up. Does that make sense why that's the case? Because let's just say you waited 5 minutes. If you waited 5 minutes with the drain shut, it'd be full. And during the same 5 minutes, would you be able to drain the whole thing? No, it takes 8 minutes to drain the whole thing. So definitely this thing would slowly start to fill. Slowly fill. Okay. So now what's the question? If the faucet is turned on and the drain is left open, how long will it take to fill the sink? Well, this is a really interesting question. So that's very different from just saying, if I left the drain shut, how long would it take to fill? If I left the drain shut, how long would it take to fill? It would take the 5 minutes that it says. But I'm going to leave the drain open so the water is draining out and it's filling at the same time. How long until it fills? Anyone want to just take a guess? It would take 5 minutes if that was shut. But if you open it and the water's draining, how long do you think it'll take? 20 minutes? Like it would have to take more than the 5 minutes. Maybe 20, maybe 15. Yeah, who knows? What are you saying, George? 40 minutes? Okay. All right, so now let's take a look at what we're saying here. We have our formula x over a plus x over b equals 1. And this problem is a little different because we're not both contributing to the same job. One of them is contributing to filling it, and the other one is contributing to emptying it. So one of these would be a positive quantity because we're trying to fill it up, and one of them would be a negative quantity because we're trying to drain it. Yep. So what we would do then is plug in. We would have, it would take 5 minutes to fill it up. That's our 5 minutes to fill. And on the other hand, it would have 8 minutes to drain it. And so that 8 is a negative. So this is the force of filling the sink, and this is the force of emptying the sink. And then away we go solving it. So let's see what we get. So we need a common denominator. The common denominator of 5 and 8 would be 40. So we're going to multiply all the way across by 40. And so 40 over 5 would be the 8x. And then 40 over 8 would be 5, so that's minus 5x. And then 40 times 1 is 40. And we end up with 3x equals 40. And then we divide up the 3. And we get x equals the amount of time it takes to fill, which is 13.3 minutes. 13.333 would be it anyway. Now I know my phone went off a little bit ago, just 6 or 7 minutes ago. Let's finish this last problem. We'll take a break, and then when we come back, we can just look at the practice test. So let's reach conclusion on this. All right. Last one. Yeah, oh, Josh, go ahead.
Why is it 8x minus 5x?
Well, the negative here makes this whole quantity negative. And then when I distribute the 40, that would really, if I distribute it right now, that's a 40x, and that's a 40x, and that's a 40 over there, right? So then 40 divided by 5 would be the 8, and 40 divided by 8 would be 5. And because that was plus or minus, that's negative. Does that answer your question or no?
It does.
Oh, it does? Okay. I mean, I can see the larger question is why did I make that one a negative? And that's because this term is contributing to filling, whereas this term is draining it. And so it's taking water out of the sink, whereas this one is putting water into the sink. Does that?
Yeah, it's just because I had the longer route, and I got that it was -8, but I also got a -42.
Oh, okay.
I just did it the wrong way.
Okay, but you see it now?
Yeah.
Okay. All right, last one. Working together, Daniel and Donnie can clean the llama pen in 45 minutes. So everyone, first, let's write down our formula here. This is shared work, x over a plus x over b equals 1. And what they're telling us is that together, they clean it in 45 minutes. So where do I put that information?
Equals 40.
What's 45? The a, the b, or the x? Because look again at the definition. X is the time they work together. A is the time that one of them works, and B is the time that the other one works. So the 45 actually goes in for X. So I have 45 on top, because that's how long they work together. And then it says, on his own, Daniel can clean the pen in an hour. Oh, now hold on a second. Again, we have units. In one time they say 45 minutes, and then a second later they say 1 hour. What should we do?
Convert it to 60.
Yeah, we just need it to be the same units. There's no miles per hour here, so there's nothing forcing us to be in hours. So we can choose. We can either make them both in minutes, or we can make them both in hours. You want to put it in minutes? Okay. So if Daniel, so we're just going to go ahead and say that this is Daniel and this is Don. So Daniel can do it in an hour, which is 60 minutes. Then how long does it take Donnie, which is my B? So there we go. X was the time they worked together. A, that was just how long it takes Daniel. The B, we don't know how long it takes Donnie. And then we go ahead and solve. So 45 over 60, that's 0.75. Plus 45 over B is 1. And we can go and subtract 0.75 over. And we get 45 over B equals 0.25. And how do you get a variable out of the denominator? Same way that we've been talking about canceling denominators. How do you cancel a denominator? Multiply both sides by it, because that way that denominator cancels out. We have now 45 equals 0.25b, and then dividing off both sides by the 0.25. We get what? 180. So what does that mean? Daniel was 1 hour, and over here Donnie was 180 minutes, which is actually 3 hours. How would you feel if you're Daniel? Now see, this is a tough one. Like, how do we interpret Daniel and Donnie? Daniel can clean the llama pen in an hour, whereas Donnie, it takes 3 hours. So you might think to yourself, boy, Daniel's really efficient, and Donnie is this great big slacker. Like, I don't want to work with Donnie. He's a slacker. Does anyone think that way?
No.
Maybe. Because there's a different way to interpret it, and that is that Daniel's the slacker. It only takes him an hour because he does a terrible job. He doesn't actually clean the llama pen very well. It's still a mess. Whereas Donnie actually does the work that is necessary, and he makes it clean. So what do you think? Is Daniel efficient and Donnie a slacker? Or is Daniel do terrible work and Donnie does the work correctly? You think highly of Donnie? But and you think that he's just cutting corners?
Yeah.
Yeah. Now, do we have any reason to believe one way or the other? We have no way of knowing. And how long does it take them if they work together? Only 45 minutes. Yeah, I'm really torn. I don't know which one of these two people I would hire.
I wonder if Daniel.
Yeah. Like, is Daniel giving him bad work habits? Like, oh, you don't have to clean that part. That's fine. Or again, yes, I just don't know. Would you want to hire somebody who takes 2 hours? Would you be like, forget Daniel and Donnie, I'm going to keep hiring, and I'm going to look for somebody who takes 2 hours to clean the llama pen? Yeah, I think we don't have enough information yet, right? Okay. All right, folks. Well, was that all the problems in the packet? Okay, so we're done. Let's go ahead and take a break. The time is 9:13. Let's come back at 9:24. And hey, everybody, go ahead and take a moment and flip through the practice test and see if there's any problems in particular that you want to look at. Because I want to show some problems to you, but you go ahead and flip through and see if there's any that you'd like to see as well. Right. So let me just yell in the hallway real quick. Come back, folks. Did everyone get the practice test? I have more copies up here. Okay, so before I start looking at the problems that I'd like to do with you, would anyone like to throw out any particular questions? Like, you've had a chance to look at it. I'm going to write down a list of problems for chapter 3 and chapter 4. Are there any in particular that you'd like to see? Because then I can make sure to hit those as well as the ones I'd like to look at. Any you would like to see? I will cover quite a few. And you know, if no one has anything right now, then we can always look at it.
Number 5.
On which one?
Chapter 3.
Yeah, 8 and
Number 5.
of chapter 3, number 5. Okay.
Number 6 and
Chapter, wait, 3? 6, okay. Okay, any others?
chapter 3, can you find number 1?
Yeah. All right, well, that's good. Anybody else have anything? If you think of some along the way, that's fine. Okay, then I will go in order, looking at the ones I'm going to look at as well as the ones that you just said. So, in the case of number 1, in number 1 it says, find the degree, leading coefficient, and maximum number of real zeros of the polynomial. The only tricky thing about this problem is the fact that the terms are not necessarily written in order. So like here, the first term is actually 5x to the 6th. And here the first term, well, is actually the first term, negative t to the 6th. So in this first problem, when they say what's the degree, the degree is 6, because that's the highest power. The maximum number of x-intercepts, therefore, is 6. The y-intercept is the constant term, which is negative 2. The leading coefficient, again, you look at the leading term, the leading coefficient is 5. And therefore, the picture of the end behavior, since it's an even function and it's positive, will simply be parabolic. And it'll look like that. So you just go on down the list and write down 6, 6, negative 2, 5, and draw an upward-facing parabola. Yeah. So now this one over here, the degree is also 6. So the maximum number of x-intercepts is also 6. The y-intercept is negative 20. The leading coefficient is a negative 1. And therefore, the picture of the end behavior would be an upside-down parabola. So you would just draw a little upside-down parabola. Celine, you asked about that one, right? Does that answer your question? Okay, great. Thanks for asking about it. All right. Let's see here. What do you need to do in number 3 in order to do this problem? 0. Well, that's true. We want to set it equal to 0 because we want to find the x-intercepts and the y-intercepts. You know how to find the y-intercept. You just plug in 0. And if you plug in 0, the whole thing equals. Yeah, well, hold on. Before you factor it, if I just plug it, to find the y-intercept, you plug 0 into the function. If you plug in 0, 0, 0, the whole thing is 0. So the y-intercept is 0. And yeah, to find the x-intercepts, you have to factor this whole thing. You have to factor it and set it equal to 0. So in terms of factoring that, let's just look at it. You have 4r cubed plus 4r to the 4th plus 4r cubed minus 24r squared. What all can you factor out? 4. A 4 and r squared. So you take out the 4r squared, leaving behind r squared plus r minus 24. And at that point, you do have a zero product rule. You have the first thing times the second thing. But we can further factor this. So what multiplies to make 24 that adds to make 1? You can do a factor table just to check. So 24 is 1 times 24, 2 times 12, 3 times 8, or 4 times 6. Oh,
Wait.
oh, not 24. That should be a 6. Thank you. Yeah, because I divided out the 4. Okay, so that's a 6. Okay, different factor table. What multiplies to make 6? To add to make 1? 2 and 3. So we'd have r plus 3, r minus 2. All right, yeah. So now each of those can be set equal to 0. And that's going to tell you all of your x-intercepts, right? So I'd have 4r squared equal to 0, and then I'd have r plus 3 equal to 0, and r minus 2 equal to 0. And then here, r simply equals 0, and here r equals -3, and here r equals 2. Whereas the previous one, number 2, this was already factored. So how do you find the y-intercept? You multiply all the numbers at the end. So 6 times 3 times 4, which would be a negative times positive times negative, that's positive. 6 times 3 times 4 is 72. So the y-intercept is 72. And then for the x-intercepts, you would set each of those equal to 0 and solve. Okay? All right. Now again, my goal is not to do every single problem, because I think we'd run out of time. But I do want to go through quite a few of them just to remind ourselves. It's been a while now. It's been at least a week or two since we've talked about chapter 3. So how about number 4? They say use synthetic division to find the quotient and the remainder. This is well worth reviewing. We're going to divide that. So I'm going to divide x squared minus, x cubed. We're going to divide x cubed minus 2x squared. Where's my x term? Yeah, plus 0x plus 21. So I'm going to divide that polynomial by x plus 2. So remember, what was our chain of reasoning here? We were saying, is this thing divisible by that? Because if it is, that means I should be able to take this top polynomial and rewrite it as x plus 2 times something else. Right? That's the question. We're saying, if this really is divisible by x plus 2, I should be able to take the entire numerator and rewrite it as x plus 2 times something. That's what it means to be divisible. So if x plus 2 is a factor, that means that x plus 2 represents an x-intercept, which means the x-intercept is actually where? At -2. Which means the coordinate -2, 0 should be on my graph, which means input, output. If I input a -2, it should give me 0. So that was the chain of reasoning to now do synthetic division. I'm going to plug in a -2, and hopefully I get a 0. So let me take my coefficients now, 1, -2, 0, and 21. And then we go ahead and do synthetic division. So I drop the 1, multiply, add, multiply, add, multiply, add. And no, I didn't get a 0. Right, so as an experiment, I'd say, well, no, x plus 2 is not a factor of this polynomial. I cannot strictly factor it like that. -2 is not an x-intercept. However, I still have useful information. What this tells me is 3 pieces of information. Since I started at an x cubed, this becomes x squared, x no x. And what I have now is that my original polynomial, x cubed minus 2x squared plus 0x plus 21, is equal to this factor. And since it's a -2, that becomes x plus 2. And then this factor, 1x squared minus 4x plus 8. And then the remainder, which is 5. So this is always what synthetic division does for you. It takes a polynomial and it reduces it by 1 factor. And the hope is that that last number is a 0. Because if it is a 0, then you actually factored the polynomial. If it isn't a 0, then that just means you have a remainder. So what do we have now then? This was the divisor, d of x. This was the quotient, q of x. And this was the remainder, r of x. So that would be the answer I'd like to see right there. The problem says use synthetic division to find the quotient and the remainder. So if you just write that out, that'll look pretty good. And I'll see that the quotient is this quadratic, and the remainder was the number 5. Questions on that? All right. So So in number 5, we did a problem like this the other day in class, but it's a really good one, and so I'm happy to do another one with you. It says here that we have a polynomial of degree 4. Now, already we can write something down. What does a polynomial of degree 4 look like? It would be p of x equals x minus, x minus, x minus, x minus, with the coefficient c out front. That would just be the most general formula that you could write for a polynomial of degree 4. You know that you'll have 4 factors, all of which with an x minus, and that you could have some coefficient out front, which could be a positive number or a negative number. And so they're saying a polynomial of degree 4 has a root of multiplicity 2 at x equals 4. So that means that 4 is an x-intercept twice. So I plug in the number 4 twice so far. And then it says it has roots of multiplicity 1 at x equals 0. So just 1, 0. And at negative 4, so just 1, 8. So far, that's what we have. And I will go ahead and clean that up. I'll say, okay, p of x is c x minus 4 squared times x plus 4. So now what do we know? We almost have our polynomial. What's the one thing we need to find? What's the one thing up here that's unknown? Yeah, the c. We need to know what that coefficient is in front. And so they're telling us how to find it. They're saying that this polynomial should go through the point 5, 4.5. So if I wanted to go through the point 5, 4.5, you look at your coordinate as an input-output. If I input 5, I should output 4.5. So if I input 5, so I'm going to take my function now and input 5, which means over here now I'm going to input 5. And if I do input 5, what should my output be? 4.5. There. And what we now did is we came up with an equation where the only unknown now is the letter c. So now we can solve for c. So what would this be then? It'd be c times 1 squared times 5 times 9 equals 4.5. And so what is that? 1 squared is 1, 5 times 9 is 45, so that's really 45c. 45c is equal to 4.5. And then c is being multiplied by 45, so you divide by 45. We get c equals 1/10, 4.1. Now at that point, keep in mind you're not done. The problem says find a formula for p of x. So now I will go ahead and write it down. So p of x is 0.1 times x minus 4 squared times x plus 4. And now that's it. That is, in fact, a polynomial that has x-intercepts at 4 and 0 and negative 4, and it does go through the point 5, 4.5. Did that work? Okay. Now, number 6 is very much like that. Only now, instead of telling us information, they're just giving us a graph. So this is really exciting. This is a really great problem. They're saying, here's a polynomial. I want you to come up with an equation that looks like that. I want you to come up with an equation that looks like that. So what can we say about it? Yeah, exactly. So we have an x-intercept at negative 4. We have an x-intercept at 3. Both of them are bounces, which means that particular factor should have an even exponent, probably just a 2. And so that's what we know so far. We also have, well, what other points do we know? For sure that's an x-intercept. For sure that's an x-intercept. I don't know exactly what any of those coordinates are, except for the y-intercept. I do know for sure the y-intercept. It looks to be a negative 1. So let's use that. Let's use all that information. What we're going to say then is in number 6, we're going to write down our polynomial. And what we know is that we started off with c, and then we have 2 bounces. So notice how I started this problem a little differently. I'm starting it off by saying the polynomial is some coefficient times x minus something squared because there's a bounce, and x minus something squared because there's another bounce. And those bounces are at -4 and at 3. So that I can clean up just a little bit. If x equals c, x plus 4 squared, x minus 3 squared. And we still want to solve for c. They didn't come right out and give us an input-output coordinate like last time, verbally saying it, but they gave us a picture of a graph, and there is one special point on that graph that we know, and that's the y-intercept. So the y-intercept is the coordinate what? 0, 1. So input 0, output 1. So I know that it should go through, I'm going to say through 0, 1. So in other words, then, if I input 0, it should output a 1. Sorry, yes, -1. Because the y input is -1. There we go. So now we have this equation to solve. Notice in both of these problems, you're setting up an equation to solve for c, because that's the one piece of information you don't know yet. All right, so that would give us c times 4 squared is 16 times -3 squared is 9, and all that equals -1. So that's 144c equals -1. And then dividing both sides by 144, we get c equals -144. And we would never convert that to a decimal, because it's going to be some repeating decimal that goes on infinitely long, whereas -144 is perfect. That's a nice, succinct, perfect answer. So we'd say our polynomial is -144 x plus 4 squared x minus 3 squared. Now, does a negative coefficient make sense? After all, what is our end behavior? It's basically a parabola, and it's upside down. So we were expecting a negative coefficient. And because there were 2 bounces, that's an overall exponent of 4, which is what we ended up with. Those 2 ended up with 4. What's the one last thing you might do? Like if you're doing this on a test and you want to know, is it correct? Yeah, you can take out your graphing calculator and go ahead and graph what you claim to be the answer. So -1 144th times x plus 4 squared times x minus 3 squared, and there's our graph. That is what it looks like. There's my -4, there's my 3, there's my x-intercept, sorry, my y-intercept, and the graph looks the same. Okay, let's see. I think the last one here I wanted to look at was number 8. Well, let's look at both of these. So in number 7, I give you a very specific list of things I'd like you to do. I walk you through and I say, do this, do this, do this, do this, do this, as a way to walk you through a full solution of a polynomial that you want to factor. So let's look at that. Oh, my numbers are different. Okay, well here, let me look at this.
So the answer key 7 for you is our number 8, and our 3 is your number 7.
Oh, I have them switched.
Yeah, that's
Oh, right, yeah. I spaced it out a little bit differently so that everybody would have more room to do their work. Right, yeah, I did. So we're about to look at, well, let me do yours in order. I'll look at your. Oh, darn. Well, I have this formatted differently then. I want to walk through all those steps with you. But for yours, it's different.
our number 8 looks like your number 7.
Yeah, it sure does.
7 doesn't look like it, it's not set up the same.
Right. Okay, well, well, actually, yeah, everybody, you're looking at number 8? Yeah, go ahead and look at number 8. Because even though that mine says 7 up there, it's the exact same problem. So everybody, let's look at your number 8 together. So let's walk our way through that problem, the 9x cubed problem. Okay. So 9x cubed. First, what does the rational roots theorem tell us? Rational roots theorem is going to be making a fraction of all the divisors of the last number divided by all the divisors of the first number. So what are all the divisors of 16? That'd be 1, 2, 4, 8, and 16. Now how did I know that? Because you can take the number 16 and do a factor table. Factor table, yeah. So 1 and 16, 2 and 8, 4 and 4. Those are all the numbers that multiply to make 16. And so I just list those numbers in order. So 1, 2, 4, 8, 16. Those are all the divisors of 16. And then I want all the divisors of 9. So same thing, I can make a factor table for 9. That's 1 and 9, 3 and 3. So I just list those numbers in order, 1, 3, 9. And while this is a little mind-numbing, I want you to sit there and list them all out. So the rational roots theorem states that you make every possible fraction. So you would get 1 over 1, 1 over 3, 1 over 9, and then 2 over 1, 2 over 3, 2 over 9, and then 4 over 1, 4 over 3, 4 over 9, and then 8 over 1, 8 over 3, 8 over 9, and then 16 over 1, 16 over 3, and 16 over 9. Right, so that's every possible fraction. That's what the rational roots theorem does. It lists out all these potential candidates that you have to find a whole number or fractional x-intercept for that polynomial. At that point, I'm pretty satisfied. Like, if you now went back through, and I would never ask you to write them in order, and you know the most we could do is rewrite some of them as whole numbers, but that's fine. That's your list of candidates. All right, so then the second part was listing out how many positive x-intercepts could you have and how many negative x-intercepts could you have. That was the Descartes' rule. Gosh, what was it called? Not rational roots theorem, it's the sign variation. What was that thing actually called? It had a name. It was called, rule of signs. That's right, the rule of signs. I'll get back. All right, so the rule of signs is let's start with P. We're going to list out the pluses and minuses for the original function. So that would be plus, minus, plus, plus. That's the original function. So how many times did the sign change? It changed once, twice, and then not anymore. So twice. So that means P equals 2, or you start subtracting by 2. So 2 minus 2 is 0, and that's as far as you go. So you either have 2 positive numbers or no positive numbers. Okay, what about n? Now you write down all the signs, but you change the signs on the odd-powered terms. So the odd-powered terms are 9x cubed. It was positive. I'll make it negative. I keep the even-powered sign. And then 32x, that's an odd term, so that's positive. I make it negative. And then the last term is also positive. So how many sign changes do we have this time? No change, 1 change. So n equals 1. And if you start there and start subtracting by 2, 1 minus 2 is negative 1, so we're done. So now we know that this polynomial either has 2 positive x-intercepts or none, but it for sure has 1 negative x-intercept. That means that on my graph, I know that I have a negative x-intercept. And then I either have 2 or no positive x-intercepts. So that's one possibility. My graph is going to look like that. Or my other possibility, my graph looks like that. Okay, now, at this point, you're allowed to use your calculator and just find the next x-intercept. So you would just plug that all into your graphing calculator. Like, I'm not going to ask you to sit there and just start trying all those candidates one after the other. You can just type it in. And if you have questions about how to graph on your calculator during the test, you can come see me and I'll show you how to graph on your calculator. But me just looking right now, I see that I have an x-intercept at negative 0.333, which is negative 1/3, or 1.333, which is 4/3, or 4. And you're free to choose any one of those. But just looking now, I see my candidates were 1/3, so that one actually works, and it's negative, so that's negative 1/3. My other candidate was 1.333, that's 4/3. That's also, that one's positive. And then my other x-intercept was a 4, and so that's positive. So there, out of all those candidates, those were the 3 that actually work. And now I'm free to choose whichever one is most convenient to go ahead and do synthetic division. So which one is most convenient? 4. Let's do 4. So we're going to go ahead and do synthetic division using my 4. And so that's the next part is synthetic division work. So I'm going to do 4. I have to write down my coefficients. It's 9, negative 45, 32, and 16. So I'll go ahead and do my synthetic division. Drop. So multiply, add, multiply, add, multiply, add. And as we expected, it was a 0, because we knew 4 was an x-intercept. And so now I can reduce my whole polynomial now to say that this is really x minus 4. And since I wasn't cubic, now I go to squared. So this is going to be x squared, x, no x. So now I have 9x squared minus 9x minus 4. That's as far as synthetic division took me. Now, what do you do when you get down to the last quadratic? We still want to keep factoring. And we need the last quadratic. Yeah, I mean, if you can factor it, factor it. I don't see a way to factor this one. So instead, you do the quadratic formula. Now, let's see how that works, though. Because technically, there's a leading coefficient right there on the 9. So let's just remember, what we're about to do is find the x-intercepts for this quadratic, but there was a leading coefficient of a 9. So what we're really going to do is factor out that 9. So you have 9 times x minus 4. And then you're going to put in x minus, and whatever answers you get from the quadratic formula, that's what you put in right here. So we're doing 2 things. First, there's a leading 9 there, so that comes out all the way up front. And then whatever answers you get from the quadratic formula is what you insert as the x-intercepts into the remaining part of the formula. So let's try that. The quadratic formula would be 9, negative 9, negative 4. So my x-intercepts are negative b plus or minus b squared minus 4ac all over 2a. So b, a, c, a. And that gives us 9 plus or minus, whatever all that is. It's 81 plus 60. I got 225 all over 18. And the square root of 225 actually comes out to 15. So that's 9 plus or minus 15 all over 18. And when you're done with the quadratic formula, you have 2 alternate realities. So I'm going to draw my 2 arrows and say on the one hand, I have 9 plus 15 over 18. On the other hand, I have 9 minus 15 over 18, which gives me 24/18 or negative 3/18. No, negative 6/18. Which both of those can simplify. This one becomes 4/3, and this one becomes 1/3. By the way, did we all talk about the math frac button on your calculator? That you can simplify fractions, but so if you type in 24 divided by 18, and then you hit math frac, it just gives it to you as simplified. Okay, so then, those are my other 2 x-intercepts. And those become the last numbers I put into my factored expression. So that would be 4/3 and negative 1/3. Now, depending on how you felt about factoring out that 9, so there was a 9x squared, I'm telling you that you can simply factor out the 9 and then put in the answers to the x-intercepts right there, but maybe that left you feeling a little uncomfortable, like, why am I allowed to just bring out the 9? Well, you could always actually bring out the 9. Okay, so you can have x minus 4, and then divide each of those by 9. So I'm going to bring my 9 out, and that would leave me with 1x squared minus 1x minus 4/9. And then you can do the quadratic formula on that. If that just makes you feel more comfortable and legit, that, okay, I now just genuinely took out a 9, leaving these numbers, and then you would do a equals 1, b equals -1, and c equals -4/9. If you do the quadratic formula with those numbers, you will get the exact same answers. Okay, you will. Maybe that'd be interesting for you to try. You know, prove it to yourself that whether I take the 9 out and use those numbers in the quadratic formula, or take the 9 out and use these numbers in the quadratic formula, either way, the quadratic formula is going to give you the exact same result, which is why you're allowed to just back out the 9 and then put in the answers from the quadratic formula. All right, well, that problem is almost done now. It said do the synthetic division work, which is also the quadratic formula work, and then finally report all of your answers. So what's the y-intercept? 16. What's the end behavior? Where's my original? So this is my answer, but the original was 9x cubed minus 45x squared plus 32x plus 16. So the y-intercept was 16. The end behavior was a positive cubic. So what would that look like? The end behavior should look like that. The y-intercept was at 16. And then we have all these x-intercepts. And then it says to draw the graph. So let's draw the graph. We would have the y-intercept at 16. So I'll go ahead and put that there. I have my x-intercepts, which I now know are at 4, 4/3, and -1/3. So -1/3, 4/3, and 4. Those are my 3 x-intercepts. And keep in mind, this is now exactly what I predicted it would look like. Well, one of my predictions anyway. So I have all this. I know that my end behavior looks like this, so I can draw one tail going up from there and one tail going down from there. And then otherwise, you just connect the dots going through the y-intercept, and there you go. So that's the end of the problem. On the test, I give you a full page for that. Well, at least I think I did. Questions about that one? About all the different work to show? Then for number, well, let's see here. For the next one. Oh, well, on your practice test, I gave you all that space for both of them. So for number 7, you also have all that space to show all that work. Then for number 8, you had all that space to show all that work. Okay, well, wonderful. Well, then, that's that. Then let's look together at number, let's see. Number 9 is just a bunch of questions about I. You can look over that. Number 10. Here we go. Number 10. Number 10, I just give you a formula, and I say, go. I don't necessarily space it out, giving you space in particular for showing me particular things. I'm simply cutting you loose on number 10 and saying, go for it. Find all the zeros, find all the x-intercepts. So now what could you do here in this problem? So let's all look at this together. So you have some function, 4x cubed minus 24x squared plus 24x minus 20. And it just says find all the x-intercepts. Now to be fair, what could you do? You're sitting at your desk, you want to find all the x-intercepts, what could you do? You can just graph it, right? You can just go right into your graphing calculator and do 4x cubed minus 24x squared plus 24x minus, I wasn't typing. 4x cubed minus 24x squared plus 24x minus 20. And by doing that, first thing I noticed is that I only have one x-intercept. It's an x cubed, so I should have 3 x-intercepts, but I only have the 1. And the one that I have is a 5. So you cannot do the whole problem by just graphing, because there's only one that I see. And therefore, the other 2 are what? Imaginary. So, but by looking at the graph, you can at least start your problem out by using synthetic division with the first 5. So let's start. Now, what other nice thing could you do? You can take out a 4. So we have f of x equals 4 times x cubed minus 6x squared plus 6x minus 5. That's just kind of nice. And now we know that this has an x-intercept of 5. So what you can do is go ahead and do the synthetic division work with a 5. And that gives you 1, negative 6, 6, negative 5. When we do our synthetic division, drop 1, multiply, add, multiply, add, multiply, add. Okay?
Would it be 5 or would it be?
It's a good question. I'm glad you asked, because I want you all to be able to reason through that on your own. If you look at the graph, and there is an x-intercept at 5, which means the coordinate 5, 0 is on the graph. Input, output, input, output. That means if I input a 5, we should output a 0. Yeah, it's a good question. Okay, so what does this give us? That gives us x minus 5, and this was cubic, so now it's squared, x, no x. So now I have 1x squared minus 1x plus 1, and that's where I'm at so far. So now my f of x, which was 4 times all that, is now f of x equals 4 times that. So we took out the coefficient of a 4, and so far we factored out the minus 5, and now we still have this. So notice we're about to do the same thing. We're about to, it's the same thing as over here. We keep the 4, we keep the x minus 5, and then we write down x minus, and what we're going to do is drop in the x-intercepts that we get from the quadratic formula. So at this point, we would do the quadratic formula of 1x squared minus 1x plus 1. And whatever those answers are, we just put them right there. So let's do the quadratic formula. A is 1, B is negative 1, C is 1. So I've got negative b plus or minus square root of b squared minus 4ac all over 2a. And now I drop in all my numbers, so b, a, c, a. And that gives me 1 plus or minus the square root of 1 minus 4 is negative 3 all over 2. So indeed, the answer from the quadratic formula was imaginary. We can clean that up a little bit, and that'll be 1 plus or minus what? It's the square root of 3 times the square root of negative 1, so that's root 3i all over 2. That doesn't look very exciting, but what we can do now is just rewrite that as 2 different possibilities. You either have x equals 1 plus root 3i over 2, or you have 1 minus root 3i over 2. Those are your 2 different x-intercepts. And as such, those are the 2 numbers that you'll drop in to the formula. 1 plus root 3i over 2 and 1 minus root I over 2. Okay, now the problem said find all the zeros and then enter the zeros separated by commas. Enter the exact value, not a decimal approximation. So on the one hand, what I've done here is I've gone beyond the call of duty and I've actually factored it. So what do we actually need to write down? The x-intercepts are 5, 1 plus root 3i over 2, and 1 minus root 3i over 2. So that's the answer. That's the answer that was asked for. Find all the zeros. So those are them. But it'd be nice if you gave that as well, right? Because this is demonstrating the bigger skill that we've learned how to do, which is to take a polynomial and factor it into a multiplication problem with a coefficient and potentially with an imaginary number. So this is a really good problem that kind of ties all that together. To which you say, oh yeah, Mr. G, that's a really good problem. Really ties it all together. But it does, right? That's a really good culminating problem. Look at how much you do in that problem. You factor out the original coefficient, you do synthetic division, you do the quadratic formula, it results in an imaginary number. You plug the whole thing in so it's nice and factored, and you're listing out the x-intercepts. I mean, it's really good. That's really good application. Okay. Well, that was it for chapter 3, which it had been 2 weeks since we've done that, so I'm glad we got to review that together. Now let's take a look at chapter 4, and I'll just go through some specifics with you. Like what you're looking to write down. Ready? So in chapter 4, we're going to go in order here. Number 1, it says determine the equation for the vertical asymptote. So where do you find information about vertical asymptotes? The denominator, right? Because wherever the denominator is 0 is either a vertical asymptote or a hole. So let's look at each one of these problems. So number 1, my first function is x cubed plus 1 over 3 times x plus 2. Okay. Now, in each of these problems, you're not going to do any cancellation, and it's not going to be a hole. Well, at least not those problems right here. They just want the vertical asymptote. So all you're going to do is find the location of the vertical asymptote, which means, take your factor from the bottom, x plus 2 equals 0, therefore x equals -2. And I want you to notice something subtle here. -2 is the location of the vertical asymptote. So when I say x equals -2, that means the x value of -2 is the x-intercept of the location of the vertical asymptote. What I'm saying is that -2 is a value that if I plug it in, it makes the denominator 0, therefore undefined. But what they're asking for is the equation of the vertical asymptote. That also is the equation of the vertical asymptote. Right? Remember that if you have a horizontal line, the equation is y equals the y-intercept. And if you have a vertical line, the equation is x equals the x-intercept. Okay? So this is very subtle. That is telling you the location of an x-coordinate. That is the equation of a vertical line. Do they look identical? They're identical, right? So I mean, this is just very subtle that I'm bringing your attention to, that when we say something like x equals -2, you could be talking about the location of an asymptote, or you could be talking about the line of the asymptote itself, or you could be talking about a number that if you plug it into the equation, it makes it true. So there's a lot of subtlety there. Anyway, that's the equation of the line. How about for the second one? You have x plus 1 over 2x minus 4. So again, I can factor that out, and it's 2 times x minus 2. So I'm factoring out the 2 if you can. So again, you set that equal to 0. You say the vertical asymptote is anywhere a factor equals 0 in the denominator. So x equals 2. That simultaneously means the vertical asymptote is at the location of x equals 2. That's where the vertical asymptote is. But x equals 2 simultaneously is the equation of a vertical line. Okay, well anyway, that's enough for number 1. You can do the last one. Okay, number 2 is saying, for each function, find the long-run behavior, which means the horizontal or the slant asymptote. So let's look at each of these in turn. So find all the horizontal or slant asymptotes. In the first one, we have x squared plus 1 over x squared plus 2. Now, first of all, how do you find horizontal asymptotes again? Yeah, you do the ratio of the leading terms, right? So let's do that for each of these. The ratio of this leading term is x squared over x squared, which is simply 1. So that means the horizontal asymptote is at the horizontal line y equals 1. Again, a horizontal line is y equals the y-intercept. This is telling us where the horizontal asymptote is, and so that horizontal asymptote is at y equals 1. The second equation is a little different. Second equation is f of x equals x squared plus 1 over x squared x cubed plus 2. So again, the ratio test would give you x squared over x cubed. And honestly, you can just look at that, and as soon as you see that the power at bottom is bigger than the power on top, you know the answer is going to be 0. The horizontal asymptote will be the x-axis itself. But even if you simplify it 1 over x and then let x become really big, like 1 over a billion, the answer is 0.0000000, essentially 0, which it is. So the horizontal asymptote now is y equals 0. So that's 2 of the 3 possibilities. If the degree is the same on top and bottom, the horizontal asymptote is whatever the ratio of those 2 terms are. If the degree is bigger on bottom, then the horizontal asymptote is automatically y equals 0, which is the x-axis. Whereas the last one, x cubed plus 1 over x squared plus 2. When the degree on top is bigger than the degree on bottom, it's automatically a slant asymptote. If the degree on top is bigger than the degree on bottom, it's automatically a slant asymptote. And while the ratio test will tell you part of the answer, the whole answer is gotten by actually doing long division. So at this point, we'd actually have to do long division. We would say x squared plus 0x plus 1 divided into, well, I need more room. A little more room. We're going to do x squared plus 0x plus 1 divided into x cubed plus 0x squared plus 0x plus 1. So we're going to do long division, and we say, looking at the first terms, what do you multiply by x squared to get x cubed? Just x. So then we multiply, so that's x cubed plus 0x squared plus 1x. And then we subtract, so we change all the signs, and we add. So that cancels, we have negative 1x plus 1, because you drop the next term. And then at this point, you can't keep going, because you're starting with an x squared, and you're saying, what can you multiply by x squared to get x? You can't. So we're actually done. And this part up here, whatever you end up with up there, is the slant asymptote. So if you look at that as the equation of a line, y equals mx plus b, it's just 1x plus 0. That's 1 over 1x plus 0. That's the equation of the slant asymptote. The equation of your slant asymptote is that. The slant asymptote is the quotient. It's the answer from long division.
Is it necessary to have 0?
Well, no, I was just being more specific.
So if you answered the question as just 1x for x, y equals x.
I would still give you credit for that. Yeah. Now keep in mind, this agrees with what the ratio test would have given us. Had we done the ratio test of x cubed over x squared, that would have ended up with just x. But the ratio test is only ever going to give you the first term. If there was a y-intercept, you'd only find that by doing the long division. Okay, so those are 3 different possibilities. Same power, you just do the ratio. That tells you the horizontal asymptote. Power on bottom is bigger, it'll automatically be the horizontal asymptote of the x-axis, where y equals 0. Or if the power on top is bigger, then you actually have to do long division. And I have one more problem for you like that, number 3. Let's do that. This one will be a little more interesting. So number 3, the power on top is bigger than the power on bottom. So we automatically know that number 3 is a slant asymptote. Now I know the question says find the equation of the vertical asymptote and the equation of the slant asymptote. The vertical asymptote we can all get. You set the denominator equal to 0, and that's where your vertical asymptote is. Let's just do the slant asymptote. So we're going to divide 2x minus 3 into 12x squared minus 16x minus 1. And again, you always look at the leading term, and you say, what do you multiply times 2x to get 12x squared? Does everyone agree? 2 times 6 would be 12, and x times x would be x squared. So we're multiplying times 6x. So you write that above, 6x, and then you multiply. 6x times 2x is 12x squared. 6x times negative 3 is negative 18x. And then we're going to subtract, so that means you change the signs and add. So those terms cancel out, and you end up with 2x minus 1. Now this you actually can continue dividing, because what can you multiply times 2x to get 2x? Just 1. So now we have multiplying now, 1 times 2x times negative 3. Then again, you subtract, so you change the signs and add. Those cancel, and you get 2. So that part on top is the slant asymptote. Which means the slant asymptote is y equals 6 over 1x plus 1. That is your slant asymptote. And if you check, it is. So we have 12x squared minus 16x minus, I'm not typing. 12x squared minus 16x minus 1 divided by 2x minus 3. There's the equation. And then if I type in the slant asymptote of 6x plus 1, I should see, indeed, a red line that asymptotes up against those two functions, and it does. And I could make my that look a little better. -3. There we go. That looks really nice. Yeah, see, you can tell that it really is a slant asymptote. Okay, now let's see. I have 5 minutes. What else do I want to go over here? Maybe number 4. Ooh, number 5. I think 4 and 5. Yeah, let me see if I can get through 4 and 5. Keep in mind, all the solutions are online. Selena? Do we what? Nope. Now remember, from a long time ago, if you want to rewrite that original problem as 6x plus 1 plus 2 over 2x minus 3, you could rewrite the whole problem. And you could say that it's actually equal to 6x plus 1 plus 2 over 2x minus 3. That is a way of rewriting the problem, but no, you don't have to do anything with it. The problem is only asking for the slant asymptote. Okay. Number 4 is a great problem. It's what we trained for. It's just giving you some rational expression, and it's asking you to detail all the information about it. So let's definitely do this one. So number 4. There's our rational expression. I'll write it down. 3x squared minus 2x minus 5 all over 2x squared minus 3x. Okay. So first, going in order of ease, what's the y-intercept? Yeah, to find the y-intercept, you just plug in 0. So the y-intercept is, by definition, f of 0, which if I plug in 0, all those go away, and I just have -5 over 1. So the y-intercept is -5. Okay, B. I want to find the the x-intercepts and the vertical asymptotes. Recall, the x-intercepts are what are in the numerator, and the vertical asymptotes are what are in the denominator. Now the big challenge here is what? You get to factor that. So that's a little bit of effort, isn't it? To sit there and factor that out. You can try to just guess as to what the answers are. Like, is it 3x, x, 5, 1, minus, plus. There we go. So there's the first one. Just to save time, because class is almost over, I'm just giving it to us. So there's the first factorization. Is that correct? Yes, it is. And then on the bottom, here's the second factorization. Again, you would have to do all this factoring yourself, but I'm just giving it to us so that we can have our answers. Okay, yeah, so there's our factorization. So what are the x-intercepts? You would need to set both of the factors in the numerator equal to 0. Yeah, exactly. So you'd have 3x minus 5 equals 0, which is 3x equals 5, which is x equals 5/3. There's one x-intercept. And then you have x plus 1 equals 0, so that's x equals -1. That's the other x-intercept. So those are our two x-intercepts. And then to find your vertical asymptotes, you set both of the factors in the denominator equal to 0. So my vertical asymptotes, all right, 2x minus 1 equals 0, which is 2x equals 1, which is x equals 1/2. That's a vertical asymptote. It is simultaneously telling you the location of the vertical asymptote as well as the equation of the vertical asymptote. And then the other one is x minus 1 equals 0. And so that vertical asymptote is at x equals 1. That's the location of the vertical asymptote as well as the equation of the vertical asymptote. So there's our vertical asymptote. And then in part D, they're just asking for the horizontal asymptote. So again, the ratio of the leading terms, you have the same power on top and bottom. So we can just do the ratio and see what it is. It's 3x squared over 2x squared. The x squareds cancel out, and you have 3 over 2, which is 1.5. So the horizontal asymptote is at y equals 1.5. Okay, I have one more problem that I want to do with this. Really? What do I have, like a minute? I have a minute. Just nobody look at your watch. I have a minute. So, number 5, it says write an equation for a rational function with all those details. So can we do it? What do we know? We're going to have some f of x with some factors in the top, factors in the bottom, and potentially a leading coefficient. So now look, we have 2 vertical asymptotes. So put those in first. My vertical asymptotes are at -3 and at 2. And then I have 2 x-intercepts. Notice how I'm doing this formula again of x minus, x minus. My x-intercepts are at 5 and -2. And finally, I want there to be a y-intercept at 8. Now keep in mind, I could have a leading coefficient up here that I don't know about. And if I'm saying that I have a y-intercept of 8, that means that on my graph, there's a point right there, which is 0, 8, which means if I plug in 0, I should get 8. So let's see how that would work out. If I plug in 0, I'll have c times 8 minus 5 times 8 minus -2, which is plus 2, all over 8 minus -3, which is 8 plus 3, and then 8 minus 2. And all that should equal 8. Oh my gosh, I just did all that wrong. I'm plugging in 0. Oh boy, I'm sorry. If I plug in 0, I'm going to have my coefficient, and then 0 minus 5, 0 plus 2, all over 0 plus 3, and 0 minus 2. All that should equal 8. So now I clean that up. I say that's really c times -5 times 2, all over 3 times -2. And all that should equal 8. So that's really c times -10 over -6, which simplifies to positive 5/3. So I have 5/3 c equals 8. All of this is to figure out my formula, or my actual coefficient. So now I can multiply both sides by 3/5, and that gives me c equals 24/5. That is my coefficient. And then I would go back, finish my problem by just writing down the formula, which would be f of x equals 24/5 x, what was it now? X minus 5, x plus 2, all over x plus 3, x minus 2. Okay, folks, that's a really good application problem. I know you haven't seen anything like it yet, but it's an application problem. Let's try to apply what you've learned about functions. And so now, if you go back and check, does it have x-intercepts at 5 and -2? Yes. Does it have vertical asymptotes at -3 and 2? Yes. And if you plug in 0, will the whole thing equal 8? It should, because we just designed it to do that. All right, folks. Well, the time is 10:20 on the dot. And if you have any questions at all, please come see me. I have office hours for the next 2 hours. I'm just going up to my office right now to wait for you. So come on up, ask me questions. Otherwise, go online to Canvas, download the solutions, go through them all. Make sure you fill out the whole practice test. And oh my gosh, now you're going to go on spring break. So how long do you have to study for this test? Oh, it's like mind-boggling. You have so much time. You just want to take the test right now? Yeah? No? No? Okay, fine. Also, go home and watch Monty Python and the Unladen Swallow. It's a very funny scene. And then you'll better appreciate that word problem. Selene. Did I say that right? I've been practicing in my head for weeks now. Selene. Okay, go ahead.
So for year 2020,
Yeah.
would it be on the outside of the function or?
Both are the same. Yeah, like consider, and actually, Selene, because you asked such a good question. Let's say that you have this thing. I won't write it on the factors. So you could either put 24/5 right there, or you could put the 24/5 out front, which means you could just put 24 on top and 5 on bottom. All of those are the exact same.
Okay.
What you cannot do is put 24/5 at the bottom, because dividing by a fraction is the same as multiplying by the reciprocal. And that, this one right here, would be the same as 5/24 on top.
Okay.
So you can't do it that way, but all three of those are correct. And then it'd be kind of neat if you convinced yourself of that. Like, what if that was just a 1 and that was a 1? Right? Are all of those equivalent to each other?
Mhm.
Yeah.
Okay. Thank
Good
you.
question. Sure. So Lena, you ran. That was impressive.